Okay, so we are recording. Now we're in section 4.7. Section 4.7 talks about change of basis. So we learned how it can be helpful to have sometimes to use a different basis than what we're used to. Like, for instance, the example where we had the crystal lattice and those basis vectors that ran along the edges. That's a convenient basis. And we want to be able to find a way to switch back from one basis to another. And that's what change of basis is about in section 4.7. So in some applications, a problem is described initially using a basis script B, but the problem solution is aided by changing this script B basis to a new basis, script C. And we saw that again with the crystal lattice problems. You know, if you want kind of a visual for this, they have a nice figure here, figure 1, where you have two coordinate systems for the same vector space. Okay, so you have in figure 1 from section 4.7 in your textbook, you have a vector x. You have a vector x, and the vector x, if it's in the same spot in both pictures, okay, it's in the same spot. You know, the origin is where it is, and the vector x relative to the origin. I mean, in both figure 1, A and B, the vector x is the same vector. But in figure A, okay, how would you write the vector x in terms of the basis vectors in that figure A? The vector x equals, I mean, well, first of all, well, I mean, looking at the picture, what are your basis vectors in figure A? B1 and B2, that's right, Benjamin. So they don't even tell you the coordinates. You know, I mean, it's just B1 and B2. So the vector x is going to be what? Vector x in terms of B1 and B2 in figure 1A is going to be what? What would it be? Good, Robin. Good, Benjamin. 3B1, good, Solomon. 3B1 plus B2, plus 1B2. So if we go along, if we do 3 times the vector B1, and then add the vector B2, that gets us to vector x. And so the coordinate vector of x relative to the basis script B is 3, 1. However, if you look in figure 1b, here they have the vector x, and your basis vectors there are clearly C1 and C2. They're different vectors. It's a different basis for R2. What you know, what would the coordinate? I mean, what the vector x equals? Okay, you read my mind. The vector x equals 6 times C1 plus 4 times C2. Hence, the coordinate vector of x relative to the basis script C equals C4. Now, what we want to do is have a way of going back from one basis to another. Okay, we want to have a way of I want to say this the right way. One moment. We want to have a matrix that will allow us to a change of coordinates matrix that will take us from one base to another base. And that's what the example I'm going to do is about. But this is, you know, just to, oh, why isn't it negative? Well, Binyam, 6, look, if you go to 6C1 and then, you know, add 4C2, that's going to get you to X. Okay, all right, good. Are there any other questions? Okay, all right. So let me go ahead and bring up an example here. Okay, and I'm going to let you copy this example. All right, take a few moments to copy that, and then we'll go over the solution. And this example really is I think it's a nice example. It really touches upon a lot of important things in section 4.7. All right, so an interesting problem. We have two bases for r squared. One's given by script B, which involves the base 1, base 2 vectors, B1 and B2 vectors, and the other, script C, involves the C1 and C2 vectors. We want to find a change of coordinates matrix from the basis script B to script C, and then we want to find change of coordinates matrix from the basis script C to script B. Right? So if we keep things simple, we you know, we'll be comfortable with this. So let me ask you: do you agree that I ought to be able to take a multiple of V1 and a multiple of V2 hold on, I got that wrong. Nope. Hold on, let me do this again. If I had the vector equation x1 times c1 plus x2 times c2 equals b1, if I had that vector equation there, would we be guaranteed to find an x1, x2 that'll satisfy that vector equation? I mean, I'm not even asking you to solve it right now. I'm just saying, should we be able to find two scalars, x1 and x2, such that the linear combination of vectors c1 and c2 equals b1? Absolutely, that's right, James. Absolutely, Solomon. Because the c1 and c2 forms a basis for R2. So any vector in R2 space can be written as a linear combination of c1 and c2. Well, the vector b1 is in R2 space. All right? Similarly, should we be able to take some linear combination of c1 and c2? Sorry. Should we be able to take a linear combination of c1 and c2? Let me rephrase it. Should the vector b2 in basis script b be able to be written as a linear combination of the basis vectors from script c? Absolutely. For the same reasons that the vector b1 in basis script b could be written as a linear combination of the basis vectors from script c. So you understand then that the x1, x2, the y1, y2 are going to be coordinates. And they're going to be x1, x2 would be the coordinates of the vector b1 relative to script c, and y1, y2 would be the coordinates of the vector b2 relative to the basis script c. All right, I'm going to go to the next page if there are no questions. Are we? All right, so how might we do this? Kevin's good. Thank you, Kevin. Well, we can actually find these coordinates, x1, x2, y1, y2, at the same time. Let me show you how this works. The book has an interesting way of doing it. What they do is they set up an augmented matrix. Well, first of all, we recognize that we need to solve these two augmented matrices. Right? We said on the previous page that we had to solve two vector equations. So each vector equation corresponds to a system of equations. And each system of equations corresponds to an augmented matrix. And these here are the two augmented matrices. But we can solve them simultaneously by simply having on the left side, you have the vectors c1 and c2. And then on the right side, you have the vectors b1 and b2. And you're going to solve this. You're going to solve this. I'm going to say this the right way. This quote augmented matrix represents I want to say this. We're not, it's really an algorithm for solving two systems of equations simultaneously. It's not like the inverse, Binyam. No, this is not like it's not like the inverse. It's like, why can't we solve these two system of equations at the same time? We do row operations to solve the first system of equations, okay, and we do row operations to solve the second system of equations. But the point is, when we solve each system, we are trying to get the left side of the system that has the columns C1 and C2. We are trying to get that left side into what form? Into what form? Now, it's actually got to be a little careful. It's the whole matrix, but I mean, what would we just love to reduce C1 and C2 into reduced row echelon form? It's the same row operations that the same row operations to find the to solve the augmented matrix C1 C2 B1 would be also the row operations to solve the augmented matrix C1 C2 B2, and that's what's being set up here. This is only to be used for section 4.7, okay, but it makes sense in 4.7. So I do my row operations. So of course, I guess I can do a little labeling here. I'm going to take here. I'm going to take 4 times row 1. Add that to row 2. And put the result in row 2. I mean, that's what I did to get this here. I had to here take 4 times row 1, add it to row 2, and put the result in row 2. Okay, which is fine. And then what do I do? What do I do to arrive here? What did we do? What do we do to the second row? Good, that's right. We took 1/7 times the second row and replaced the result in the second row. And, you know, the row operations help, you know, I find it does help students stay centered with the linear algebra. And these are simple row operations. Okay, so, you know, you're always thinking, right? It helps reinforce concepts. Now, finally, to get the 3 here, what do we have to do to get, to get a 0 in that spot? We have to take what? We have to take, good, Binyam, good, Sagan. We have to take -3 times row 2 and add that to row 1. And put the result in row 1. Okay, and as a result, you get your x1, y1 coordinates and your y1, y2 coordinates. You get the both coordinate vectors. So, and the entire matrix, okay, the matrix on the right with 6, 4, and -5, -3 is called your change of coordinates matrix from the basis script B to the basis script C. And we denote it using this symbol here. So in terms of our notation, the coordinate vector B1 relative to the script C basis is 6, -5. The coordinate vector of B2 relative to the script C basis is 4, -3. And so the change of coordinates matrix from basis script B to basis script C is going to be 6, 4, -5, -3. And that will allow you to well, let me let you copy that down. So we're doing part A here in our solution. This is all part A that we're doing here. Okay. So it's like we're preferring now to use the script basis C. That's why, and the coordinates we get are for the vectors B1 and B2 in terms of the script basis C. That's why you have an arrow going from, in the notation, the subscript, you have the script B, but you have the arrow going from script B to C. Now, what might be the next thing we might want to ask? What's the next natural thing to ask? Could we find the change of coordinates matrix from script C to B? That's right, Binding. Well, we could do that. That's right, Solomon. We could do that. We could go through the same process that we did. It's just, we would have on the left, instead of C1 and C2, we'd have B1 and B2, and then on the right, we'd have C1 and C2. But is there maybe another way to get it? Well, let me just mention here. Let me inverse. Mikkel's right. That's right. So let me go to the next page. Are we good here? Any questions? All right. So I need to have a little something here. So if we take the change of coordinates matrix from script B to script C. Try that again. Okay. And let's see here, hold on. One moment. Okay, and we multiply that by let me rephrase it. Sorry, I want to rephrase it. Let me write it like this. So the coordinate vector of x relative to the basis script c will be equal to the change of coordinates matrix from script b to script c times the coordinate vector of x relative to the script b basis. Now, that makes sense. If we want to find, so this is, we're really doing part B now of the problem. If we want to find the change of coordinates matrix from script C to script B, all we need to do is multiply this equation on the left side by the inverse of the change of coordinates matrix from script B to script C. And that change of coordinates matrix will be invertible. And so you end up then getting a formula. Well, you have in this step here, you have the coordinate vector of x relative to script B is going to equal, I'm just kind of rewriting it, the coordinate vector of x relative to script B equals the inverse of the change of coordinates matrix from script B to script C times the coordinate vector of x with respect to the script C basis. But this inverse of the change of coordinates matrix from script B to script C is simply then called your change of coordinates matrix from script C to script B. That's how that is. That's what it is. Now you could find that change of coordinates matrix from script C to script B, doing the, you're doing the row operations, but another way to do it is to just recognize that it's, you can use the inverse. And so when you do that, you're going to get this result. And if you did row operations, you would get the same result. Are there any questions on that? Okay, so the notation can be, the notation is helpful, but, we always want to keep our fundamentals in mind, and that's why, that's how I like to do things. And I think you do too, right? Hope so, right? How many of you love the fundamentals? Okay. Wow, a lot of thumbs up, and that's great. That's great. Thank you, everybody.